ready to get started. So for the midterm one, we have finished the regrade request and everything. So later this week, I'll transfer all your grades from Gradescope to Brewing Learn. So make sure I have your grades correctly transferred. And make sure you finish the survey again, 1 extra credit, just to let me know how you want us to calculate that 150 grade. And I also received your second chance for problem 521, and your TA and I will grade it later today. So it's basically, I recognize the fact that our midterm one is really too long. I think everyone is making that opinion very clear in that midterm one survey. So that 10 point is a little bit of remedy to that midterm one being too long. And I promise you your midterm two will be slightly shorter. Okay, that being said, we're ready to move on to our today's lecture, where we're gonna pick up from where we left over from chapter 4. So chapter 4, from here, everything will sound a little bit abstract. So again, you'll feel like we're doing all these derivations using equations after equations. So just bear with me and try to follow what are the logic behind it. And eventually we'll get to a point that you'll find out, okay, so the whole purpose of thermodynamics is to use these relationships that seemingly abstract to convert something you want to measure to something that actually experimentally can be done. So for example, what we did before is, in our last lecture, is to make the connection between chemical equilibrium and two new state functions, which are our Helmholtz free energy, A, which is defined to be U minus Ts, and also the Gibbs free energy, which is G, defined as enthalpy minus Ts. All right, so what we know is we know entropy is maximized at equilibrium. And by defining these two new state functions, we say, okay, so these two state functions will equal, the change of these two state functions will equal to 0 at equilibrium. So let's look at some examples first, and then we'll look at the physical meaning of these new state functions. Like, what exactly are our new state function, Helmholtz free energy and Gibbs free energy, and why do they call free energy? Let's get started. So this one is one of the textbook example that we have. I don't remember which one is it, but it's one of your textbook example. And let's just work out how to calculate your delta G and delta A for a specific process. So if you don't have your iPad, again, take a picture, because we'll be moving away from this problem. Let's just read it together. The question asks you to find delta G and delta A for the reversible freezing of 1 mole of water at 0 degrees Celsius and 1 atm. So basically it's at equilibrium at that 0 degree Celsius for water freezing. And we're considering only PV work that's being done in the process. Some of the things that you will need, including the heat of fusion and the heat capacity of water at constant pressure, the density of ice, and also density of water at that given temperature and pressure. So it asks us to calculate delta G and delta A. And in this process, we're dealing with a reversible freezing at constant pressure. So our reversible freezing tells us my ds equals to dq reversible over t. Right, and in this case, it's just the change of dq freezing. And at constant pressure, we actually know that delta H equals to QP, which is delta H freezing equals to QP equals to Q freezing. You all have a copy of this problem, right? So I can just moving on. All right. And then a few things. Let's start from delta G, because, well, it comes at the first. So we know delta G equals to delta H minus T delta S. So that comes from its definition here. We know it's at constant temperature, so we take temperature out from that integration. All right, so we have G is by definition equals to H minus Ts, and at constant temperature and pressure, your delta G equals to delta H minus T delta S. Actually, let me just not skipping any points, any steps. So we have G by definition equals to H minus Ts, right? So what we have is dG by definition equals to dH minus dTs. And you can rewrite this out to be dH minus TdS minus SdT. And in here, we know this term goes to 0 at constant T. So we have dG equals to dH minus TdS. And you take integral on both ends, you get delta G equals to delta H minus T delta S at constant temperature and pressure. Well, at constant temperature, but pressure will come back later. And at constant pressure, we have delta H equals to QP equals to Q freezing. All right, so that is at constant pressure. We know information about what delta H is. So taking together, what we end up getting is here your delta S, as we know, actually equals to delta S, T delta S equals to Q freezing. That's by the definition of S entropy equals to dQ over T, right? So we have T delta S equals to Q freezing, and your delta H also equals to Q freezing. So that tells us this all thing goes to 0. So your delta G equals to 0 for this process. With me so far? All right. Next up, let's move on to look at delta A, which is the Holmes free energy. So likewise, doing the same kind of logic, you can end up having delta A equals to U minus Ts, right? So delta U minus T delta S at constant temperature and pressure. And in here, we solved this before, right? T delta S equals to Q. And this delta U, well, that's our first law of thermodynamics. In a closed system, your delta U equals to Q plus W. So this gives you Q plus W minus your Q freezing. So your delta A effectively equals to the reversible work that's being done in this process. And at constant pressure, you can rewrite that pressure out and do the derivation. Equals negative P delta V. All right. And then the problem becomes a simple algebra problem, right? We know the density, we know the mass of your water in ice form or in water form. You can calculate the volume, initial volume, and the final volume for this freezing process. And by calculating the initial and final volume, you have delta V, and you can plug in numbers to find out what is the W reversible. So let's think about this problem. If you see this problem in the exam, everything till like now, without doing any calculation, just simply set up the process, simply set up the reactions, you'll probably get like 60% of the grade. And doing that correct calculation counts only like 40% of your grade. So if you're running out of time, you can just pause here and like write out, like I know what V initial is. Like for example, you can write V initial equals to M initial over rho initial, and V final equals to M final over rho final. And just don't have time to plug in numbers, that's all right. You lose like 2 or 3 points, but you get the majority of the point. If we see, you know how to set up the problem. Okay, I'll leave it for you to work on that mathematical problem. You can check your answer with the annotated note. But the take-home message here is just read the question and know what are the things to use, right? For example, in here, just read the question, just because we know it is a reversible process, we have ds equals to dq reversible over t. And at constant pressure, we have delta H equals to Q for this process. All right? Any questions before we move on this problem? Nope? Okay, sounds good. Next up, we'll spend just a little bit more time thinking about how is your delta S of the universe related to the Gibbs free energy of the universe for the process. Again, we're looking at the system. We've seen it before. We're just imagining you have a system of interest that's separated by a, well, impermeable wall, but not adiabatic, so heat can go in and out between your system and surrounding. So in this process, let's think about what is happening, right? So for the change of entropy of your surrounding, it's always equals to Q surrounding over T. All right, and the reason we can say it is even if we have irreversible reactions taking place within the system, as long as the heat transfer between the system and the surrounding is slow, your surrounding is always at equilibrium. And in this case, we have the heat of surrounding equals to negative heat of the system. So this is something we've done before in our previous lecture. And in here, what do we know? Assume we have constant pressure. So your delta H equals to QP at constant pressure, or your delta H of the system equals to Q system. And we can plug in that number to get delta S surrounding equals to negative delta H of the system over some temperature T. Let's assume at constant Tp. That's easy. So for this whole process, what we care about is the delta S of the universe equals to delta S of the system plus delta S of the surrounding. And this is given by just the extensive nature of entropy as a state function. And in here, we have delta S of the system plus what we just derived here. So your delta S surrounding equals to negative H system over T. All right, and here what we want to know is how does your equilibrium actually connect your Gibbs free energy with entropy? So what we have is, again, your Gibbs free energy is by definition H minus Ts. So we can write delta G equals to delta H minus T delta S at constant temperature, which is effectively the same to say delta S equals to delta H over T minus delta G over T. All right, we're just moving the terms, assuming constant temperature. And then what we have delta S system, thus equals to delta H system over T minus delta G of the system over T. Right, that's just using the definition of your Gibbs free energy. And then we have this term here equals to here. And obviously these two terms will cancel out. What we end up having is delta S of the universe equals to negative delta G of the system over T for this closed system. Constant temperature and pressure, and PV work only. So again, it looks like a lot of limitations to that relationship, but if you think about a typical chemical reaction at room temperature and like atmosphere, so it is pretty easy to achieve this kind of relationship, right? You have a cylinder containing some kind of chemicals reacting with each other, right? So you have irreversible chemical reactions taking place in the system. And the delta G of that system links to the overall delta S of the universe. Or the other way to put it is a decrease in your system's Gibbs free energy will have a proportional relationship with the total change of entropy of the universe. All right, so a decrease in your system's free energy means an increase in your entropy. So we went over all these derivations. Now the fun part is a little bit of the addition here. So I always want to ask you this question. What exactly are these state functions? We went over internal energy, so that is just the energy of your system which is at rest without any external field. That's just energy. And enthalpy, we went over the definition of enthalpy. That is talking about the heat transfer at a constant pressure. So what about the nature of these two free energies? And let's look at it one by one. The first one, our Holmes free energy, is also called the work function. And why it is called a work function? So let's go back to our stage one. So remember what we did before. Let's go back here. The Holmes free energy, yeah, here we go. So this is where we start. We're talking about delta U is always smaller than or equal to T delta S plus dW for a closed thermal and mechanical equilibrium with material and phase changes. We went over the derivation to get like A is by definition U minus TS, and we went over that equals to 0 for something at equilibrium with only PV work. So let me just copy paste that down. So that's where we start. Now, from here, when we're rewriting these terms, let's use this one again. So we have TdS equals to dTs minus SDT. And our du is smaller than or equals to dTs minus SDT plus dW. Or the other way to put it is du minus Ts smaller than or equal to negative SDT plus dW, or your dA smaller than or equal to SDT plus dW. All right, so everything you should be pretty familiar about like how we're doing it. Now, assuming we're at constant temperature, we have dA to be smaller than or equals to dW. And that work can be any form of work, not only PV work. Or we're talking about a process of infinite process or finite process. You can take the integration of both ends. We get delta A smaller than or equals to work. And here the work is like the work done on the system. Or you can write delta A also equals to the negative work by. So here, these two differences just depending on whether or not your system is doing work on the surrounding or vice versa. So here your delta A is always smaller than work done on the system, or it's always smaller than the negative of the work done by the system. Or you can rewrite this relationship to negative delta A, and we're moving that, or flipping that sign to larger than work by. Or that's the same to say that your work by is smaller than or equal to negative delta A. So what does that mean? What does that tell us? So when you think about this process, what we're talking about is the work done by the system on the surrounding for an isothermal process in a closed system is always less than or equal to the change of its work function. So that is why your A is called a work function. It gives you the maximized amount of work your system can do on its surrounding. Now this work includes all forms of work, like PV work or electric work or magnetic work. But it tells you the maximum of total work your system can do on the surrounding. All right, so that is the physical meaning of your Holmes free energy or work function. All right. And well, this kind of conceptual question, you can expect them to show up more in multiple choices or true and false. So know the physical meaning of these terms will be very helpful. Next up, Gibbs free energy. Now we use Gibbs free energy a lot in chemistry, and let's see what is the physical meaning of Gibbs free energy. Again, what we're using here is the definition of Gibbs free energy, which is H minus Ts. So we are just writing it out. So Gibbs free energy equals to H minus Ts. And we know that H is by definition U plus PV, right? So we can rewrite it as U plus PV minus Ts. Your A equals to U minus Ts. So here, U minus Ts, that gives you your A plus PV. So here what we're doing is just rewriting your Gibbs free energy in forms of your Holmes free energy, which we just derived, which is A plus PV, just using all the definitions on the board. Now, next up, we're taking the derivatives on both ends. So we have dG equals to dA plus dPV. And we can write that out as dA plus PdV plus VdP. So some of the things we know, like dA is smaller than or equal to negative SdT plus dW. So this is something we derived here, right? So that's the dA equals to negative SdT plus dW. And with that in hand, we have the relationship of dG smaller than or equal to negative SdT plus dW plus PdV plus VdP. All right? And for a typical constant temperature and pressure process, which is very easy to achieve at our normal condition, so some of the terms goes to zero. So we have this term, the dT term goes to zero. The VdP term goes to zero at constant temperature and pressure. So we end up having dG smaller than or equals to dW plus PdV. Now in here, if you think about it, what is your dW? That is the total work done on the system. And what about our PdV? For a reversible process, we have the W equals negative PdV. So what we end up having is your dg equals smaller than or equal to dW, that is non-PV. Right, so your delta G, your dg gives you the change of work that is non-PV that's being done on your system. Or if we're doing the same thing as we did before, doing the integration and talking about how much system is done by this, how much work is done by the system, like what we did with the almost free energy, we end up getting dW by and non-PV work is smaller than or equal to negative delta G. Or when we write that out, we have the work done by the system, and its non-PV work is always smaller than or equal to negative delta G for constant TP reversible process and closed system. So what is the physical meaning of your Gibbs free energy? So now when we're looking at the number, the delta G number, so that gives you the maximum possible non-PV work. So when you're talking about a chemical reaction, right, we don't really care about how much your substance or how much of your solution or your reactant expand in the process. That part of the work is normally not an effective chemical work we want. Now, what we want are typically forms of like chemical energy. Like in your biological systems, you have energy that your body can use, right? So those type of non-PV work, like electric work, magnetic work. So these are the type of work that we can utilize. So these are the non-PV work. And your Gibbs free energy tells you how much your system can do those kind of non-PV work for a chemical reaction process. Okay. Any questions on the physical meaning of our Helmholtz free energy and Gibbs free energy? Nope. Okay, sounds good. And then we're moving on to our chapter 4.4. So I have to admit this part of the chapter is very dense in derivation and also equations. So we'll play around with all these 6 basic equations and get to some very interesting relationships between these state functions and also coefficients and everything. Now, the idea here is that all thermodynamic state function relationships can be derived from 6 fundamental equations. So here are the 6 fundamental equations I listed on the board. So these are like, if you can only bring 6 equations to the exam, please bring these 6 equations. That's all. It's like they're just very important, and we will be using them to do all the derivations later today. For example, let's get started by looking at some of the alternative expression for your heat capacity Cp and Cv. So by definition, we have Cx. Now x, that's the variable that's being held constant, either volume or pressure, equals to dqx over dt. Right, so x is the constant. And using our second law of thermodynamics and also definition of our entropy, we have ds equals to dq reversible over T. Or we can write dq reversible equals to TdS. So what that means is if we're only considering reversible process, we can rewrite our Cx, where x means it's at constant, well, x. We have T dsx over dt. And again, that x subscription just tells you, okay, that's the change of entropy at constant x. So now replacing that x with either volume or pressure, we have our Cv equals to T, partial derivative of x over T at constant V, and Cp equals to temperature times partial derivative of S over T at constant P. All right, so here we're just replacing, instead of having the subscription in your normal derivative, we'll just rewrite it as a partial derivative at constant V and P. Okay. Next up, now we're gonna start using our basic equations to derive something we called a Gibbs equations. So basically, it's asking us to write the expression of du, dh, dA, and ds for this process. Now we start from du equals dq plus dw. And that's our first law of thermodynamics. And when we read it, we know it's reversible process, PV work only. So we can rewrite this one as your Q equals to TdS, and your dW equals to minus PdV. So this one, the first part is using the first law of thermodynamics, and then that's just the nature of your dq and dw under the given conditions. All right. And then if we write our dH, now by definition, we have H equals to U plus PV. And we have H equals to U plus PV. That's what we used. And rewrite out using calculus, we have dH equals du plus PdV plus VdP. And here we have our expression for du equals to TdS minus PdV. So rewrite it out. We have TdS minus PdV plus VdP. Right, so these two PdV terms cancel out. We have dH equals to TdS plus VdP. TdS plus VdP. All right. Next one, dA. Now dA equals to, or d, u minus ts. That's also by definition. And we rewrite it out. We have du minus TdS minus SDT. And we have the relationship du equals to TdS minus PdV. Minus TdS minus SDT. All these two terms cancel out. We got dA equals to minus PdV minus SDT. And finally, we have our dg. Likewise, we write it by the definition of g, which is h minus ts. That's dh minus tds minus sdt. We have the expression of dh equal to tds plus vdp. So we can cancel out these two terms, have dg equals to vdp minus sdt. So a few of the things, for example, if we have constant p and constant t, we have dg equals to 0. That's also something we derived earlier today. Okay, so these four equations are called Gibbs equations. It's a set of equations. Now, using this set of equations and also the nature of our derivatives, we get some very interesting relationship. So now what we're doing is using these equations to derive a relationship between your state function and the partial derivatives. So, for example, when we're looking at U, the internal energy, we know U is a function of variable entropy and volume as a function of S and V. Right, so your du is dependent on entropy and volume. So writing that out, what we have is just writing out the derivative here. So what we're doing here is just write out du, write out that total differential equation. So this one is effectively the same as saying like we have some kind of function dx as a function of a and b. You write out the partial derivative of x over a constant b dA plus partial derivative of dx over b at constant a dB. So that's just writing out the total differential of your function x. Okay, so in here, what we have is writing out u, writing out that total differential for your internal energy u. So the partial derivative of u over s at constant volume, ds, plus partial derivative of u over v at constant entropy, dV. That's just writing out the total derivative. And then in here, looking at these equations, we also have a relationship of your TDS and P. So what we have here is this partial derivative of your internal energy U over S at constant V is actually the same as your temperature. So your state function temperature, the nature of your state function temperature, you can also understand it as the partial derivative of your internal energy over entropy at constant volume. All right, and the same applies to your pressure. Your negative P equals to du over dV at constant entropy S. Okay, so we have a lot more derivations. So let's just work on it on the board just to make sure we're following everything here. So in our du part, what we have is rewrite your du as a partial derivative of u over s at constant v ds du over dv at constant s dv. So what we have here is t equals to this partial derivative of du over ds at constant v. A negative p equals to that partial derivative. do the same for our enthalpy. So what do you have? We have dH as a function of S and P. So dH equals to partial derivative of H over S at constant P ds plus partial derivative of H over P at constant S dP. So again, this step, we're just writing out the total differential of enthalpy, which is a function of S and P. And looking at our relationship, we have T and your partial derivative of H over S as constant P in front of ds. So what we have is T equals to partial derivative of H over S at constant P, and your V here equals to this partial derivative. dH over dP at constant S. All right, so what is the nature of temperature? So we're always talking about the nature of temperature. What is temperature? So temperature is a partial derivative of some form of energy, whether it's internal energy or enthalpy, and over the change of your entropy. So that's why we have our thermometer temperature at the beginning, then replace it with the gas law temperature, and eventually we end up to the nature of temperature as a state function. So temperature is something like you feel like, okay, I know, we know what's the temperature of today, but the nature of temperature is deeply related to entropy. All right? And you can do the same for the rest of these two equations. We have that derivation done in our annotated note, but eventually what we end up having here is we have negative P equals the partial derivative of A over V at constant P, and negative S equals to partial derivative of A over T at constant P. And same here, we have V equals to dG over dP at constant T, and S, negative S equals to dG over dT at constant T. All right. I agree that today's lecture is more on the abstract end. It takes a little bit of time, so do try these derivations just from the standard basic equations and make sure you follow every step along the way. Now, the next point comes to view is why are we doing these thermodynamic properties? Like what exactly we're talking about? So again, we've been talking about it several times. For example, the whole purpose of thermodynamics is that we want to measure things that are seemingly difficult to measure, like entropy, Gibbs free energy, Holmes free energy. We know they're important, right? It tells us information about, well, entropy tells us information about how far you are from equilibrium. Your delta G and delta A tells you how much work your system can do. And well, how exactly are we going to measure it? Like, for example, things we can measure are our thermal expansivity and also isothermal compressibility. Like, these are the things we can measure. Now, thermodynamics gives us a tool to link these things we can measure with these complicated relationships that we don't know how to measure. I don't think I have time to finish it. Let me just introduce one of the calculus backgrounds, which is the Euler's reciprocity relations. And then next lecture, we'll go over one or two derivations together. So this one is a calculus review. So when we're talking about a function, like some random function z, which is dependent on x and y. So here we're rewriting that differential equation as some kind of function m dx plus n dy. Now in this case, our m equals the partial differential equation of z over x at constant y, and n equals to partial derivative of z over y at constant x. And then what we have is when we're working with partial derivatives, for example, if we're looking at the second partial derivative of dz over dx, and the order of taking that partial derivative does not matter when we're working on the second partial derivatives. So we have dx over dz over dy. All right, so this one is basically, you can see the proof of this one in your calculus chapter 1 section. Basically what it says is the order of your partial derivative does not matter. And in here, what we have, our partial derivative of z over x at constant y is effectively your m. And likewise, the partial derivative of z over y, that's your n. So what we end up having is partial derivative of m over y at constant x equals to partial derivative of n over x at constant y. So we're just using the nature of your partial derivative, that the order of your partial derivative does not matter. So whether you take that partial derivative with x first or y first, that does not matter. So how does that apply to our Maxwell relationship that we just derived before? So it gives us some relationship between these partial derivatives. So let's use our internal energy as an example. So for example, when we have du equals to TdS minus PdV. All right, and remember what we just derived using the Euler equations is dz as a function of x and y equals to m dx plus n dy. So in this relationship, what exactly do we have? It's z, x, y is the same as u as a function of s and v. So in here, our m equals to t, n equals to negative p, your x equals to s, y equals to v. All right, with me so far? And then using our Euler's equation, what we have these two partial derivatives to be the same with each other. And, well, effectively what we are having here is your partial derivative of m, which is t, over y, which is v, at constant x equals to partial derivative of n, which is p, over x at constant y, constant v. All right, so try that same operation and to get what we call the Maxwell relationship between these partial derivatives. And the four list is here. Using the four Gibbs equation, du, dh, dA, and dg, you can get all these relationships. And next lecture, we'll see how do we use these relationships to find out, for example, the dependence of your internal energy for volume, temperature, and also your Gibbs free energies relationship on your different properties you can measure. So today's lecture is more abstract, so do take your time and practice on things we did not do and get familiar with the process.